And again, thank you for coming to San Jose City College.
Thank you. Okay, first I'd like to introduce Mark Jacobson. Mark is Director of Atmosphere Energy Program and Professor of Civil and Environmental Engineering at Stanford University. He's a Senior Fellow of the Woods Institute for the Environment and of the Precourt Institute for Energy. Received his BS in Civil Engineering and AB in Economics and an MS in Environmental Engineering from Stanford in 1988. He received an MS, a PhD in Atmospheric Sciences in 91 and 94, respectively, from UCLA and joined the faculty at Stanford in 1994. He develops and applies computer models to understand air pollution, global warming, and renewable energy resources. He has published 2 textbooks of 2 editions each and 140 peer-reviewed journal articles. Do you have any spare time at all? He received the 2005 American Meteorological Society Henry G. Houghton Award and the 2013 American Geophysical Union Ascent Award for his work on black carbon climate impacts and the Global Green Policy Design Award for developing state and country energy plans. He has served in an advisory committee to the U.S. Secretary of Energy, appeared in a TED Talk, appeared in the David Letterman Show to discuss, David Letterman Show, to discuss converting the world to clean energy, and co-founded the Solutions Project. While he says hello, I'm going to get his presentation showing.
Well, thank you for that overly generous introduction. So what I do want to talk about today, and briefly because I only have like 20 minutes or so, are these clean energy plans that we've been developing for states and countries. And to get that going, I just want to give them motivation for this. Well, why do we care? Well, from our point of view, we're trying to solve air pollution and climate problems and energy security problems. So air pollution causes 4 to 7 million premature deaths worldwide each year, including about 63,000 in the U.S. and about 13,000 in California. And global warming is a growing problem that's estimated to cost, just U.S. emissions alone, are estimated to cost the world about $3.3 trillion per year by 2050 due to all sorts of impacts on coastlines and agriculture and water supplies and air pollution itself. And increasing energy use is resulting in increasing air pollution worldwide and higher energy prices on average. And eventually, with fossil fuels, we're going to get to a point of economic, social, and political instability. So we do need to have a transition. The key is to do it sooner rather than later. Just to give you a quick idea, this is what a lot of the world looks like. This is Beijing. But it's equivalent in a lot of cities, mega cities of the world, to smoking 2 to 3 packs of cigarettes a day. And these are the lungs of a teenage non-smoker in Los Angeles who died in a car crash in the 1970s. So that's what it was like in the 1970s in Los Angeles, except it's actually worse now in many parts of the world. So this is a serious problem that we're trying to address. It's not just climate change, it's actually also air pollution and energy security. And just a couple more graphs on the problem. The global temperatures here, 1 degree Kelvin or Celsius warmer than in the early 1900s on average worldwide, but over the Arctic you can see we're up to 4 or 5 degrees Celsius warmer than we were before, and that's causing melting of the Arctic ice, which may disappear entirely within 10 to 30 years and cause a positive feedback which will accelerate global warming. The problem is much worse than people think in terms of climate, because this is the net observed global warming, which is around 0.8 to 9 degrees Celsius now. That's really, these are the greenhouse gas warming, which is more than twice that. And fossil fuel and biofuel soot particles, which are the second leading cause of global warming after CO2 itself, they're enhancing warming. These are particles that cause air pollution problems. But there are also other types of particles in the air that cause air pollution that cause the premature mortality, so we call cooling particles that are reflective and enhance cloudiness. And they mask or hide about half of global warming in the system. So if we clean up all the air pollution, we're first going to clean up these particles, cooling particles and fossil fuel soot particles, and that will result in a doubling of the warming of the planet immediately. So the key is, well, you can try to reduce air pollution and by putting filters on cars, but that's only going to be slow, and that's not going to address the greenhouse gases. or we can eliminate all the greenhouse gases and the particles simultaneously, eliminating air pollution and eliminating climate problems simultaneously. So that's really what we need to do. And the only way to do that, though, is to change the energy infrastructure of states, countries, and the world. So that's what I want to talk about next. So we've looked, whoops. I think I'm out of the talk somewhere. So we're looking at wind, water, and solar energy solutions. So we've determined from previous studies that the best technologies for addressing these problems in terms of reducing air pollutants and climate problems while minimizing land use and water issues are wind, water, and solar. So our idea is to electrify everything and have some hydrogen where even the hydrogen is produced from electricity. And so there are four sectors that we deal with: electricity, transportation, heating, cooling, and industry. So everything's electrified. So the raw source of all power will be wind, water, solar. Wind, solar photovoltaics, concentrated solar power, geothermal power, hydroelectric, and tidal wave. And this is it. We don't have any biofuels in our program. We don't have any nuclear power. There's no natural gas. There's nothing except clean, renewable energy sources. So it has to be both clean and renewable. Clean means no combustion and no burning of things that have carbon in it, in particular. And so for transportation, for example, everything would be electrified again. You'd have either battery electric vehicles or hydrogen fuel cell vehicles where the hydrogen is produced by electricity. And there would be some cryogenic hydrogen for aircraft. So that would be the hardest thing to change. But, you know, the space shuttle itself ran on cryogenic hydrogen to get into space. So this is an existing technology. For heating and cooling, we'd use heat pumps and electric resistance heating and some solar hot water preheating. For industry, everything would be electrified as well. Now, we need some kinds of storage because the wind doesn't always blow and the sun doesn't always shine. But the storage that we'd have would have to be low cost. So in our program, well, while batteries would be nice, they're really expensive right now, in order of $600 per kilowatt hour storage. But there's a lot of low-cost storage, lower-cost storage, including concentrated solar power with a phase change material to store the material. Because for concentrated solar power, you focus light off of mirrors onto a central tower to heat a fluid, and that fluid can then be stored and used at night to heat water to run a steam turbine to generate electricity. So you don't need, you can produce electricity pretty much any time of the day or night with concentrated solar power. And we'd use existing hydroelectric, which is a form of storage, and pumped hydro, existing and proposed pumped hydro. For heating and cooling, we'd also store in water, so sensible heat storage, and the ice. And for example, Stanford University, we've had a big ice cube under a building since 1998 that was used for cooling. And now, in fact, we just shut off. We just eliminated 80% of our carbon emissions by shutting down the natural gas plant, and now using heat exchanging, some more sensible heat storage, ice storage, and solar and geothermal to replace 80% of the carbon emissions from the whole university as of the end of last month. And we'll also use seasonal heat storage in soil. So there's a community in Drake Landing, which is in Alberta, Canada, which is really cold in the winter. Well, during the summer, they collect heat, and they've been doing this for 8 years. There's a whole community. They collect heat in glycol solution on the roofs of all the homes, and that heat is then transferred to the soil through water. The water goes down, the hot water goes down into boreholes, heats the soil to about 80 degrees Celsius, and that heat is stored until winter, and everything's run in reverse, and that provides 90% of the home heating in that community. So this is an existing low-cost storage. To give you an idea, battery storage is about $600 a kilowatt hour. Soil storage is less than $1 a kilowatt hour. Then for transportation, we'd also have hydrogen and also industrial processing, some hydrogen, and we'd use demand response management also to manage the grid. Now, can we actually power the world with wind, water, and solar? So we've done a lot of numbers, especially for the U.S., but for the world, the world power demand in 2010 was around 13 trillion watts or terawatts. It'll go up to about 22 terawatts in 2050. But if we convert everything to wind, water, solar, we reduce power demand significantly. in addition to having end-use energy efficiency improvement. So we can reduce power demand 33% worldwide, with about 26 percentage points of that due to just the efficiency of electricity over combustion. For example, an electric car, the plug-to-wheel efficiency is 80 to 86%, so it's 80 to 86% of the electricity in the car goes to move the car, the rest is waste heat. Whereas in a gasoline car, about 17 to 20% of the energy in gasoline is actually used to move the car, and the rest is waste heat. So just by going to an electric car, you reduce the energy demand by a factor of 4 to 5. You need 1/4 to 1/5 the energy. That's why driving an electric car only costs 80 cents a gallon equivalent gasoline, whereas gasoline's around $4, at least it was. And so you can save huge amounts of money, about $20,000 if you drove an electric car for 15 years, 15,000 miles per year, $20,000 in fuel costs at those prices of gasoline. But you also get a reduction of energy demand as a result. It's significant. In the U.S., it's 36%, with about 30 percentage points due to the efficiency of electricity. And in California, it's about a 41% energy demand reduction just by electrifying everything. So without changing your habits, you get a significant reduction in demand just by electrifying. Now, this is the number, how many devices would we need to power the entire United States for all purposes? And so we did actually individual state plans for all 50 states, and this is the sum over all 50 states of what we would need to power the whole U.S. in 2050 for all purposes. This is not just electricity, it's transportation, heating, cooling, and industry as well. So, and then under this plan, this is not unique. There are many possible plans. We'd have 31% onshore wind, about 19% offshore wind. So 50% of wind would power the entire U.S., or power half the U.S. About 4% residential rooftop PV, a little over 3% commercial government rooftop PV, about 31% PV power plants, about 7% CSP power plants, 1% geothermal, about 3% hydroelectric, and 0.5% tidal plus wave. Now, the rooftop solar, that's actually putting solar on about 70% of all the south-facing roofs in California. So this is a significant penetration of rooftop solar. So if we can do more, that would be great, but you'd have to make more roofs. It's just there's so much rooftop space that you can use. This is the land area required to provide all this power for the United States in 2050. Now, the green is the onshore wind, and most of that is just open space that can be used for multiple purposes. So it could be on farmland, rangeland, open space land, pasture land. And the red on the bottom, that reddish orange, that's the PV plus CSP land area. And then in Los Angeles, there's the rooftop PV area. And then you have offshore wind would be, well, it'll all take up space offshore. So we're talking about less than half of 1% of the U.S. for the footprint, which is new land on the ground, which is mostly for solar, and about 1.7% of the U.S. for spacing, which is space between wind turbines, which can be used for multiple purposes. So that doesn't account for the removal of all the other energy technologies, all the pipelines, all the refineries, oil wells, all the gas fracking wells, coal mines, all the land that's taking up. For wind resources, well, there's plenty of wind to power this is solar. There's plenty of solar to power the entire world multiple times over. So there are about 340 terawatts of solar over land in high solar locations, compared to about 15 terawatts is what we need in 2050. So you have over 23 times more solar than you need for all end-use purposes in 2050 worldwide. And you have about 5 times more wind over land in high wind locations than you need to power the world. So you can power the entire world on either wind or solar, but not much else. You can't actually power it all on geothermal or hydro, because most of the hydro is actually built out, and a lot of the geothermal is just, if you went really down into the earth, you could, but it's just so expensive to do that. So wind and solar are going to take up the majority of everything that you're going to do to power the world, but you need other things like hydro and geothermal and tidal wave to help along with the process. Now, we did a study looking at, can you actually keep the grid stable with wind, water, and solar? And the first step was, well, let's take a climate model, put in the 500,000 wind turbines that we need to power the United States, and see how much energy are we actually getting, because they're competing for the same wind. When you put in all these wind turbines, they're competing for the same energy in the wind. So we actually had to simulate what's the actual energy output, and then we did it every 30 seconds for a 6-year period. And so this just shows the total power output on the left of those 500,000 turbines, which was about 0.9 terawatts total. But then this on the right shows the change in the power demand due to accounting for that competition. So you lose about 8.5% of the power with all these turbines to accounting for this competition among the turbines for the same energy. So we did but we also got out of this the time series every 30 seconds of the wind, and we did the same thing in the same model. We calculated the solar everywhere in the U.S. every 30 seconds, and then we combined that with the power demand, the projected power demand in the U.S. over time. I mean, every hour in 2050. And we combined these into a grid integration study, and we found by combining the storage with the variable solar and wind and demand response and using hydrogen, we can exactly match power demand with supply over the entire U.S. So what this shows is 6 years of results, but it shows the monthly average, but we have it broken down into every hour and every 30 seconds. But on the top, it shows every month comparing the supply, which is the red, the wind and the solar and everything else, and the blue, which is the demand plus the storage plus the losses, and they match exactly. There's no loss of load. So we were able, because this is the biggest criticism of using wind and solar, the wind doesn't always blow, the sun doesn't always shine, the lights are going to go off, everybody's going to have chaos because you can't keep the grid stable. But we're able to show now that you can, with the system, an optimized system of wind, solar, and all these other renewables, plus storage and demand response, low-cost storage, you can have a completely reliable grid. So the top shows it for 6 years, the bottom shows 4 particular days each hour, and you can see the same thing. You're matching the load. And this shows another 4 days, and it breaks down the wind, water, and solar on the middle one, and then the bottom is the load and the losses and the storage. It's hard to read that, but you can see again the top, there's another 4 days of where we're matching exactly. So this really dispels a myth that you can't have a reliable grid with 100% renewable energy system. Because the utilities never want to change anything, and so they always make the excuse, oh, the lights are going to go out and it's going to be too expensive. But this was only 11.5 cents a kilowatt hour to power the entire U.S. grid in 2050. Now, we did plans for individual states, so here's a California plan. I'm not going to go over all the numbers because I don't have time, but there's actually a website I can show you at the end where you can look up each state and find every state plan, and we've now done 139 countries of the world. So here's for China. This is a wind, water, solar plan, how to power China for all purposes in 2050. And so in this case, it would be with 16% onshore wind, 18% offshore wind, more rooftop PV and solar PV. They have more hydro as well, so I'm not going to go into all the details. I do want to talk about costs. What are the costs of energy right now? And these are unsubsidized costs of energy, and they range, right now most wind is 3.7 cents a kilowatt hour, and there is a range up to 8 cents a kilowatt hour. That's just in the worst location. But it's mostly between 3.7 and 5 cents a kilowatt hour. Now, and wind is the lowest cost form of energy in the United States today, by far. I mean, because combined cycle natural gas is 6.1 to 8.7 cents a kilowatt hour. So it's twice the cost of Great Plains wind right now. And utility scale solar PV is 7.2 to 8.6 cents a kilowatt hour. It's actually competitive now with natural gas. Whereas residential and commercial PV is much more expensive. It's 2 to 3 times more expensive, respectively. Or commercial and residential, 2 to 3 times more. But in gas peaking, if you use gas for peaking, it's actually 18 to 23 cents a kilowatt hour, so it's much more expensive too. So it's another myth that we need natural gas, and that it's such a low price that it keeps the U.S. stable, because wind is actually the least costly form of electricity today in the U.S. Yeah. Wind and solar price for the part? No, this is the levelized cost of the wind itself. But the last study I showed you, where we combined wind with storage and solar and transmission, long distance transmission, demand response, and projected through 2050, that was 11.5 cents a kilowatt hour. But that's also including, this doesn't include, for example, transmission and distribution, which is like, distribution itself is like 3 cents a kilowatt hour. But the fossil fuel structure, the fossil fuel cost in 2050 was similar. There's about 11.5 cents a kilowatt hour with their projected 2050. But in addition, the fossil fuels have another 6 cents a kilowatt hour of externalities, the health and climate costs. So the direct costs were pretty similar between a whole system of wind, water, solar, and a fossil fuel system. But then if you account for the climate and energy and the air pollution costs, then there's no comparison after that.
Mark, I have one other question from online. Do these projections take into account population increase?
Yes. Yeah, the 2050 numbers take into account not only population increase, but improvements in technology. So when we compare, like, the business as usual case, so which I haven't really talked about here, if we didn't convert to wind, water, solar, we account for, in that, even technological improvements in fossil fuels and the fact that there would be some natural conversion to cleaner energy. So, yeah, we're comparing a complete conversion to a 2050 trajectory where it's based on EIA, the Energy Information Administration projections for 2050, which account for population improvements in technology and changes in fuel types and things like that. It's very detailed. Well, we don't have carbon sequestration. We don't need it in these plans. So yeah, there's no carbon sequestration in our energy plans. Yeah.
I apologize. Sometimes I might repeat the question from the audience just so the web folks can hear it as well. Just wanted to, if I double up the questions, just.
Okay. That's fine. So then, what about jobs? So we did calculation of jobs in each state using the NREL GenI models, which look at each energy technology, the number of megawatts we produce, and then they have calculations of how many jobs would be produced, and we'd get about 4.5 million U.S.-wide. We get 4.5 million construction jobs, which are 40-year construction jobs, and about 2.2 million 40-year operation jobs. So it's a total of about 6.7 million jobs produced, and we'd lose about 4 million jobs in the fossil fuel and nuclear industry. So we think there's going to be a net job creation to this conversion, at least over the next 40 years. Now, after that, like construction jobs will go down, but you'll still need to continuously construct more. And then in terms of a transition timeline, well, the business as usual timeline is the top. If we don't do anything, then the projected U.S. demand, you can see that it's like in 2010, the projected demand was about 2.4 terawatts, and it's only going up to 2.6. And that's because there is an increase of population, but there's also an improvement of technology. That's why it doesn't like skyrocket. But if we do the conversion, then we can go down the improvement due to electrification, just due to electrifying everything, is 0.7 terawatts, or around 30%. And then another 0.2 terawatts due to end-use energy efficiency improvement. And that gets us to the 100% line, which is what we want to power by wind, water, and solar. And we expect that by 2030 we can get 80% of this conversion if by 2020 all new energy in transportation, heating, cooling is clean. And so we want to do a full conversion by 2050. Now we presented this result, or we had published a plan for California, and we presented to the Governor Brown staff in October, which proposed 80% by 2030 and 100% by 2050. And in January, Governor Brown announced in the State of the State address that he was going 50% by 2030. So he adopted about 60% of the plan, which was we're pretty happy about. Now, 2 years ago, we presented also to Governor Cuomo of New York, and he asked us to provide 5 first steps about what he could do. And he actually adopted 3 of them, which was to put $1.5 billion into solar rooftop, $1 billion into a green bank, or vice versa, and 10,000 charging stations in New York to try to get this going. So, it's slowly starting to get some traction, but it's really hard to really you know, reach politicians and try to provide them with information that might really help. And plus, you know, as you'll see, one of my conclusions near the bottom, you know, one of the biggest barriers is lobbying and politics. You know, we don't think there's any technological or economic barrier to actually getting this implemented. It's really social and political. But just to summarize, we reduced power demand by 36% in the U.S. by doing this conversion. We'd eliminate 63,000 air pollution deaths, which are equivalent to about 3% of the GDP of the U.S. in terms of the cost. And we'd also eliminate by 2050 $3.3 trillion, based on the latest social costs of carbon, of global climate costs just from U.S. emissions alone. And we'd create more jobs than we destroyed. We'd use less than 0.5% of U.S. land for the footprint and another 1.7% for spacing. And we can get a low-cost, reliable system for everything for 11 to 12 cents per kilowatt hour. That's in 2013 dollars. But there are some barriers, which are upfront costs, transmission needs, and lobbying and politics. Just to some websites if you're interested in. So we've developed this group. Well, we develop these science plans at Stanford and at other universities as well, helping out. And then we're trying to get these plans, we're trying to educate the public about them and policymakers and business people, and we do that through this group we call the Solutions Project, which is an NGO that really is designed to do just that, is to take this information and promulgate it to the public. And there's a map where you can go on and click on a state and up pops a plan. It's at the solutionsproject.org. There's also some other ways that this group gets information out there. But probably more importantly, if you want to see the actual papers on these plans, there's this complicated website you can go to that has the actual plans and the Excel spreadsheets that have, so you can get every single detail you want for every plan and see every single assumption. Hopefully it's 100% transparent. Yeah.
Question. How much of a cost would it be relative to our current energy costs?
Well, the cost in terms of levelized cost of energy is 11.5 cents a kilowatt hour. Well, you mean the upfront costs? What are the capital costs? So just to put in perspective again, the capital costs are what you need up front. Well, wind, water, solar has higher capital costs than fossil fuels, but they have zero fuel costs. But that's why you need to use the levelized cost of energy to do a fair comparison. But you do need capital to get it going, which would be spread out over 40 years. But the total cost in the U.S. would be around $13 to $14 trillion for the wind, water, solar devices, another $2 trillion for the storage. So it's on the order of $15 to $16 trillion. Worldwide, it's on the order of $100 trillion. But to put that in perspective, the fossil fuel industry spends somewhere between $5 and $7 trillion every year on the fossil fuel infrastructure. And so the payback time on the world scale is on the order of 15 years. So, yeah.
You're focused on that question in California, thinking that was Governor's office, we got to 50%. You have some estimate of the capital cost that is going for what you proposed to him, which is 8%. And he adopted 50%. What is that going to cost California to get to that?
And the question is, what are the costs if it was directly California?
Well, in the U.S., I mean, I could look it up and give you a precise number, but I just have to estimate it here. So, because the U.S., as I mentioned, was, for the total thing, including storage to be reliable, was on the order of 15 to 16 trillion. And so California is, what percent of the energy is a good question. Yeah, I would just use that number as a ballpark, 10 to 15% of that total. But again, that's the overstretched over. And actually, California might not, because California actually already has a lot of renewables, so a lot of it's already sunk. So I mean, when I say a lot, not a lot, but more than most states. So yeah, so it doesn't have to go that far. But yeah, it would be on the order of 10 to 15% of that. Yeah.
You described that you'd be able to reduce demand by electrifying by about 30%. Is that just from the waste heat or is there more?
It's mostly that. There's also the fact that you don't need, for example, refineries, and I mean that's kind of a small part of it. Yeah, you don't need refineries and some fuel processing, so there's a lot of energy that's lost in those sectors right now. That sector right now, but it's mostly in transportation. So if I actually broke down the efficiency improvements by sector, yeah, it's by far mostly in transportation, although there's also some benefits as well in the other sectors of in heating, cooling, and industry, mostly transportation. Yeah.
I'm surprised you don't have a biogas component to this at all. I think you've got some methane coming off landfills in particular, and some of the other waste streams out there. Have you thought about integrating that, or is there a reason it's not there?
Yeah. Well, there's certain types of biogas that we probably wouldn't object to. I mean, anything that you burn, we object to, I guess. So if you're burning it, then we don't include it in the plan. The only exception for burning is cryogenic hydrogen for aircraft, because there really is nothing else you can do. You can't put a battery electric aircraft except for really small at this point. But there is, if you can get methane from a landfill and use it like in a fuel cell, that would probably be good, because otherwise it would be waste. It would go into the atmosphere anyway. So that's a good. I think that would be an example of something that would be reasonable. But we haven't. If that is used, that could be included. But it's we haven't quantified that for these purposes, because we're just looking at can we do everything without that. But if we can do that as well, and that can only reduce the demand for other energy.
There's a couple webinar questions. One is clarification on CSP. You had a map up, and then on that map you had PV and CSP. Yeah, CSP is concentrated solar power. So this is these are solar plants that are usually in desert regions that you have mirrors surrounding a central tower receiver that contains a fluid, and the mirrors heat up the central tower and the fluid to extremely high temperature, and it's usually like a molten nitrate salt or some other material. And then you can store that heat overnight and use it to heat water to create steam, to run a steam turbine to generate electricity. So CSP is also technology you can use for storage. Yeah.
Can you actually look at identify all the urban areas where the load is, and all the geographical areas where the water and solar plants will be, and all the transmission infrastructure that has to be built?
No, well, our model for dealing with the grid integration assumed perfect transmission, but we did assume also that we would need to spend money on long-distance transmission. So we assumed there was the baseline was like 30% of all energy, all wind, water, solar would have long-distance transmission of like 750 to 1,000 kilometers. So that was included in the costs and also the losses of energy. But we didn't model explicitly the transmission grid in the U.S. because that would be impossible computationally because of it's just, if you get into the modeling of load flow modeling and transmission, trying to do what we're doing, it's just, you'll find out that it's really impossible to do at this stage. Yeah, it's a nightmare.
The other question I had is that you showed that generation follows the load pretty good on the national level.
Right.
And that's sort of by common logic that everyone's saying that it's not there, we need it, etc. But I think that statement that wind and solar is not available when you need it still applies in the local utility jurisdiction or in the area. So this solution that you're suggesting would probably require a national grid operator to be able to move the energy where it's needed versus where it's generated. That thing doesn't exist today.
Well, we think actually that you can get the same solution on a regional scale. I think you're correct if you narrow it down to a small state, not California, but let's say take one small state, and you couldn't get inflows and outflows of energy into that state, then you would have more problems. But the system that we're modeling here is different completely than the system today because all sectors have been electrified. So we have lots of heating and cooling loads that are included, and we have hydrogen that we can store. So when we actually have, a lot of times right now when we have extra wind and extra solar, it's just shed and wasted. But in our system, it would either be dumped into producing hydrogen or put into soil storage for heat. So, in fact, in Denmark, that's what they do. You know, they have lots of extra wind, and that extra wind is used to heat the cities. And so this is, yeah, it's a different paradigm so when we have too much wind and solar, then it's actually easy to store in either hydrogen or heat or transmit it to some other location. And then when there's too little, then we do have enough storage. We've actually sized the storage for like CSP, and we have hydroelectric, we have pumped hydro for electricity, and then we have underground heat storage to reduce the demand. So we can produce like cooling, we can produce ice, for example, from electricity, but that ice, then we do that at night when the electricity is cheap, and then during the day, when we need air conditioning, which usually is generated from electricity, we instead use the cool from the ice to produce the cooling, and so that reduces the demand. And then on top of that, we have demand response. So there are actually a lot of tools in this tool chest that can, over a region, you can satisfy this grid. So I agree that on a really small scale, it would be hard, but on a moderate scale, we don't need to do the whole U.S. But our next step is actually to model smaller regions and maybe kind of mid-sized countries.
So can we take a look at the model? Is it available?
Well, we're just publishing the work now, but it will be, everything's going to be transparent, so eventually it will be available, but right now we're still going through the publication process, so not quite yet. But everything will be described, and that part will be available for the description, but the actual model probably a little bit later.
Wonderful. Any other questions, folks? Great. Thank you, Mark.